Welcome back. Now today we'll discuss on surface defect. In the previous lecture video, we already discussed on the crystal defect and the difference between the crystalline material and amorphous material. And yeah, as we know that crystalline defect, there are basically three types of crystal defect that occurs within the material. Now number one is that is basically point defect, that is also called zero dimensional defect. Second one is basically a line defect, that is basically one dimensional defect, and that is basically screw dislocations, edge dislocation. This type of defect are basically called uh, line defect. And the third, which we'll discuss today, that is surface defect. Okay. Now, surface defect is basically, we can say that these defects are basically two-dimensional defect, as it is occurs within the surface of the material. So that's why it is called surface defect or two-dimensional defect. Okay, and it happens on the surface of the material. Now, what is the main cause of the surface defect? So first, in main cause of that, main reason is first is imperfect packing of atom during crystallization. Imperfect packing of atom during crystallization. So atoms are not packed within orderly fashions. Okay. Now during crystallization, what is crystallization? Now, crystallization is the process in which old crystal structure deform and it turns into it forms into a new crystal type of grain. That is called basically crystallization. So in this process, the new grain are formed. So in this process, the packing of the atom packing actually, that is basically imperfect in nature. So that's why the surface defect may be occur. This is the first reason. Second case is that the defective orientation, defective orientation of atom throughout the surface of the material. That's the main, one cause for the surface defect. Okay. Now, as you know that the surface defect are basically three types of surface defect are occur within the surface of the material. Now, first one is grain boundary. Now, grain boundary are one type of defect in which actually the grains of different orientation separate the general pattern of atom. That means, suppose this is a crystal structure in which you can see that suppose this is the atom's orientation in this manner. Okay, the atom's orientation in this manner. So this is the general pattern of the atom. Okay, now in between the crystal structure of the atom, there are another pattern which is seen in your diagram is a bluish color actually. That is the pattern is different from the other two side of the orientation of the pattern of the atom. So this is the difference. So that form a grain boundary which actually differentiate the atoms of different orientation of atom. That is basically grain boundary, and that is one type of defect. Now, what is the cause of grain boundary defect? Number one, cause is basically during the solidification of liquid metal. That means when the liquid molten, when the actually solid metal is transformed into actually liquid, so liquid metal is transformed into solid metal. That process is actually called solidification. So during this time, when the atoms are arranged, so at that time the grain boundary defect are occurs. Okay. Now, grain boundary defect are basically, there are two types of defect are there depending on the misalignment or disorderliness of the atoms during the surface of the material. Now, number one, if the grain boundaries misalignment is less than 10 degree, that is called basically low angle grain boundary. So low angle grain boundary is that type of grain boundary defect in which the misalignment or disorderliness of the atom is basically less than 10 degree. It is called low angle grain boundary. Okay. And it is basically if the low angle grain boundary is formed by edge dislocation. Now, as you know that line defect, there are two types of line defect. One is screw dislocation, another is edge dislocation. Now, if the low angle grain boundary is formed by edge dislocation, then it is called tilt boundary. Okay, so this is called tilt boundary, and otherwise, if it is formed by screw dislocation, then it is called twist boundary. Okay, so the misalignment may be in angle of less than 10 degree, or it may be greater than 10 degree or 15 degree. If it is less than 10 degree, that is called low angle grain boundary. If it is happens greater than 10 or 15 degree, then it is called high angle grain boundary. Okay. Now, second one is that second defect is that twin boundary. Okay, so twin boundary is one type of surface defect which occurs in the surface of the material, but the twin boundary is seen as that is defined when the atomic arrangement of the one side is surrounded is actually is somewhat actually mirror image of arrangement of atom other side. That means suppose this is the atomic arrangement. So this is the atomic arrangement which you can see that this is the atomic arrangement. Okay, this is the atomic arrangement. Now this is the atomic arrangement, but this type of atomic arrangement is mirror image of this side. So this side is mirror image of this side. Along the difference is that, so this is the twinning boundary which defined the mirror image of the two atoms plane. So atomic arrangement of one side, so the atomic arrangement of one side is somehow mirror image of the arrangement of other side. So this is the other side of the arrangement of the atom. So this is the mirror image, and this to differentiate one boundary that is called twinning boundary. So this is basically twin boundary. Okay, just a minute. So this is your twin boundary which different the arrangement of atom mirror side. Both are same, but they are defined just there are like a boundary that's called basically twin boundary, and the plane is called twinning plane. Okay, so this is very important. And stacking fault, this is surface defect, also it is called surface defect. Stacking fault. Now stacking fault is that type of surface defect in which the stacking of atom not in proper sequence. That means suppose there are atoms are there one in crystal structure. Now if you see that the atoms are arranged in a particular fashion. Now if the arrangement of the atom is like that, ABC pattern, ABC, if the arrangement of atom follows this chain or follows this pattern, that means ABC like this. So this is the atomic arrangement. So ABC. So this is the perfect crystal in which the atomic plane, the arrangement of atom is in proper sequence. Now, if something it happens, that it maybe happens during the solidification, during the imperfect packing of atom, during crystallization, it may be happen due to defective orientation also. Now, if it didn't happen so, there are one atomic plane or one atomic arrangement of plane is missed. So that will happen that ABC, AB and AB. So there is no C plane. So due to missing of C plane, so there will be some disorderliness will be occur within the surface of the material or within the structure of the crystals of the material. So it may happen that this atomic arrangement are not in proper sequence. That will be defect, and that will be seen in your surface of the material. Okay, so this is that three types of surface defect which can occur within the surface of the material. That defect is called surface defect. Number 1, grain boundary. Number 2, twin boundary. And number 3, stacking fault. Okay. So this is the new topic, determination of crystal structure. Now we already know that crystal structure basically within the material there are 4 types of crystal structure are there. One is simple cubic crystal structure, body center cubic crystal structure, face center cubic crystal structure, as well as hexagonal closed packed crystal structure. Okay. Now you have to determine the next topic. This topic actually determination of crystal structure. How do you determine of crystal structure? Okay. Now a basic tool which is required to determine the crystal structure is that number 1, you can use a Bragg's law to determine the crystal structure. Second, X-ray diffraction. Third, electron method, and fourth one is neutron diffraction method. Okay. Now you know that crystal structure are various simple cubic. What is simple cubic crystal structure? In simple cubic crystal structure, you already know that the atoms are arranged in such a way that in 8 corners of a cube, the atoms are situated on the corner of the atom. Okay, in the corner section. So that is called simple cubic. Similarly, body center cubic, similarly face center cubic, as well as body center and hexagonal closed packed crystal structure. Now you can use this structure. You can use to determine the crystal structure like this through different types of technique, by using different types of technique. Now, first of all, we will discuss on Bragg's law, which is basically in your syllabus. Now, what is Bragg's law? And Bragg's law is principle that that path difference is equal to an integral multiple of wavelength of X-rays. Now, in Bragg's law, actually, X-ray are basically used to determine the crystal structure. Okay. Now, the main difference is that path difference is equal to an integral multiple of wavelength of X-rays. So, this is the statement of Bragg's law. Now, suppose this is the plane of atomic plane. Suppose this is the atomic plane. Okay. Suppose these are the atoms are here. So atoms are here. Okay. So these are the atom in plane one. There are atomic arrangement are there. So these are the atomic arrangement. Okay. So these are the atomic arrangement. Plane two also and plane three also. Plane one, plane two, plane three. Right. Now, if there are some excess of their incident, some angle. Now there are incident X-rays are there. If it is incident on a particular plane 1 and with angle that you can say that glancing angle or incident angle, that is basically theta, and after there are some X-rays are there which is basically deflected with same amount by angle of theta. Okay. Similarly, it can happen so that X-rays also like B X-rays, if you name that B here, so B X-rays here also incident on a particular angle, that basically incident angle, as also you can say that this is basically glancing angle. Now if it is the angle with theta angle, then also deflected X-rays. Okay. Now these are the plane 1, plane 2 and plane 3, and D is your interplanar distance. The interplanar distance means the distance between two planes. Now that is designated with small d terms. So this is small d here. Now this is the incident X-ray, this is the deflected X-ray for plane 1. Similarly, for plane 2, this is the incident X-ray which name as B. After deflected, that name is basically here. Okay. Suppose this is your C and D. For B X-ray, when it deflected, that name will be D, and for A is incident X-ray, when it deflected with angle, that angle will be same, because incident angle and deflected angle will be same. Okay, that theta and both also theta. Now, if you draw the normal, or if you extend the line, okay, if you extend the line here, so it will be cut at a particular BY line, that will be in X. Similarly, if you draw the extent of a O line to the dy, that will be OX, that will be cut in the X. So that is basically it is basically form a triangle. Similarly, it will form a triangle. Okay. Now, if the incident angle is theta, if deflected angle also theta, so this angle also theta, because this is the opposite angle. Similarly, this also theta, that will be also theta. Now, if you draw a diagram, if you draw a triangle, actually, if you draw a triangle, suppose this is your triangle, this is O, this is X, this is Y. For triangle OXY, sine theta, this is angle theta. So sine theta, it will be is equal to XY divided by OY. Right? Now OY is the interplanar distance, that is basically D. Now OY, in terms of OY, you can write D. So XY is equal to D sine theta. See, in similar fashion, if you assume that O, X and Y, sorry, O, Z and Y is a triangle, and if you calculate the value of the YZ value, so YZ will be d sine theta in some similar fashion. Now, the Bragg's law statement was that the path difference is equal to an integral multiple of wavelength of X-rays. That means the total path difference. That total path difference is that this is the path difference. Okay, this is the total path difference is that XY plus YZ. So total path difference is equal to XY plus YZ, that equal to total path difference. Now this total path difference, that will be d sine theta. In terms of XY, you can write d sine theta, and in terms of YZ, you can also write d sine theta here. So total path difference will be 2d sine theta. Now this 2d sine theta will be equal to the integral multiple of wavelength. So integral multiple of wavelength. So this is 2d sine theta is equal to n into lambda. Lambda is basically the wavelength of X-rays. So 2d sine theta is equal to n into lambda, where d is already you know that is the interplanar distance d here. Sine theta, theta is the incident angle, or you can say that it's a glancing angle, okay, and you can say so that this angle also called Bragg's angle, okay, and n is your order of plane, means if it is incident on a plane 1, that is n is equal to 1. If incident ray is basically in plane on the incident on a plane 2, that is n is equal to 2. Similar fashion, it will be n is equal to 3, 4 like that. And lambda is basically wavelength of the X-rays. Okay, so this is the Bragg's law. 2d sine theta is equal to n lambda, which states that the path difference is equal to the, so this is the path difference is equal to the integral multiple, integral means n here, multiple of lambda wavelength. Okay, so 2d sine theta is equal to n lambda. It is used to determine the crystal structure. Okay, now let's take a numerical on Bragg's law. So this is the numerical. So go to this first, the numerical. First go to the problem. The problem says that X-rays with a wavelength of 0.58 angstrom. Okay, X-rays with wavelength of 0.58 angstrom are used for calculating D200 in nickel. So the material which is used to determine the crystal structure, that is basically nickel here. Now, the wavelength of X-ray is given, that is 0.58 angstrom, okay, and the interplanar distance, you have to calculate the interplanar, basically it is used to calculate the D200, okay, and the reflection angle that is given, that means theta is given 9.5 degree. Now you have to calculate the size of unit cell. The size, as you know that in any type of crystal structure, the size of unit cell basically determined with small a. Okay. Now, so lambda, from this numerical, the lambda value is given 0.58 angstrom. Now theta is 9.5 degrees is given. Now you have to calculate the size of the unit cell. You know that the perpendicular distance between the origin of the cube and the plane that is basically d is equal to, already proved that d is equal to a divided by under root of h square plus k square plus l square. Now d200 means h is equal to 2, k is equal to 0, l is equal to 0. So in terms of that interplanar distance for the plane D200, that will be a divided by under root of 2 square plus 0 square plus 0 square. So d is equal to d means here d200, okay. So d means d200. So that will be d200 will be equal to 0.5a. Now, according to the Bragg's law, you know that according to Bragg's law that 2d sin theta is equal to n lambda. Okay. Now 2d sin theta is equal to n lambda, and the value of theta is basically the angle. The angle means this reflection angle. You can say that the Bragg's angle that you will put on theta is equal to 9.5 degrees here, and d200. Now d200, that means 0.5a. You already calculate this. So put this value 0.5a into sine 9.5 degree. It is given in the numerical. So sine 9.5 degree, that means that value is coming 0.165. Okay, that equal to n lambda. Here n is equal to 1 because this is the plane 1. We assume that the basically incident angle on the plane, that is plane 1, or first degree of angle, first degree of plane. So n is equal to 1 lambda. Now lambda value is given that lambda is equal to 0.58 angstrom. If you put this one, you can get the value of a. A will be 0.498 angstrom. So this is the size of the unit cell. Okay. Now just please tell me. So this is the what is the atomic packing factor? What is the atomic packing factor of different crystal structure? Can you tell me? So what is the different crystal structure? What is the different crystal structure of, sorry, what is the atomic packing factor actually? What is the atomic packing factor for different crystal structure? So we already covered on this topic, atomic packing factor. Now please tell me, for simple cubic, for body center cubic, for face center cubic, for hexagonal closed pack. So these are the different crystal structure For simple cubic, atomic packing factor. Which one? 0 for simple cubic, it will be 0.52, right? Second, for body center cubic, that will be 0.68. For face center cubic, that will be 0.74. For hexagonal close rack, that will be 0.74 also. So these are the atomic packing factor. Okay. Now let's do. Here is for one assignment for you. Just try yourself in your homework as homework. Okay. We'll discuss in the next lecture video. Just a minute. Calculate the Bragg angle. Calculate the Bragg angle if 111 plane of a cube A is equal to 3.57 angstrom crystal are exposed to X-rays. Wavelength is given as wavelength is 1.54 angstrom. So this is the homework for you. So try yourself. We'll discuss in the next lecture video, and also we'll discuss in the next lecture video on crystal structure. That is basically the strengthening mechanism and the critical resolve shear stresses. Okay. Thank you very much for listening and watching me.